All right. Well, welcome everyone to How to Electrify Without Panel Upsizing. The reality is, as we move to electrify our existing homes and even potentially smaller commercial buildings, I imagine we're going to run into the issue of panels not being able to handle this. And so a couple different ways. Of course, you buy a new panel, and there's Inflation Reduction Act funds to some extent for um, the cost to cover electrical wiring and some other things, though it's still very expensive, especially in light of the fact that you're electrifying. That's very expensive. So the other alternative is we had another session, and you can go back and check that out. There are certainly systems that you can purchase to swap out the breaker box with a different kind that's still the same service. So you can certainly do that. There's, of course, a lot of cost there. Or with what we're going to be talking about today are some more lower cost, do-it-yourself friendly approaches to be doing that. So I'm super excited to be having this conversation to advance the electrification movement in our existing building and existing housing stock. Now, before we get started, I wanted to say how excited I am to share we're going to be hosting our next certified green home professional training. This is version 2. The first one is 3 years old now. We're going to be hosting it live in Grand Rapids, Michigan, but you can also call in virtually. So there'll be a live or virtual option. We'd love to see you in GR, but we understand you can definitely call in as well. You can learn more and sign up at greenhomeinstitute.org/CGHP 930, otherwise September 30th. And again, before we get started, a huge thanks to our platinum sponsor, Rheem. Obviously, if you're having trouble electrifying in the heat pump section, they have their 120 volt water heater plug and play. This works without any of the backup element resistive heating elements. And so if you're too concerned to do that, they have their full Proterra models as well. They're 240 volt that have the backup heating as well. These are up to 400% efficiency. I've had one now for over 5 years. My mother just got one installed, the 120 volt. These work great, super energy efficient, no emissions, and you can control them right from your phone. You can set them up for time of use to keep them from heating or heating too much on peak. There's so many great things these can do, and there are Inflation Reduction Act tax credits for them as well. So go to greenhomeinstitute.org/REAMHPWH to learn more. All right. So again, welcome everyone to How to Electrify Without Panel Upsizing. This course is brought to you by the GreenHome Institute. The GreenHome Institute is a nonprofit with a mission to empower people to make healthier and more sustainable choices in the renovation and construction of the places we live. Today, I will be your moderator. My name is Brett Little, and I am the education manager here. This course is approved for multiple continuing education units, including our certified green home professional designation. Got a couple too many logos there, but it would only be under the energy and health pillars. AIA Health, Welfare, and Safety may make it applicable to your state-based design or contractor license. Check out the Passive House code that pops up at the end or on your certificate to get your certified Passive House consultant certificate. So with that, I am super excited to hand it off to our speakers today. Sharon Armstrong, I think this is your third, maybe fourth time on our show over the last several years. I've kind of lost count now, but it's been a few times. So it's always great to have you back on, as well as Tom Kabat here from both from Redwood Energy. So Sean, Tom, welcome, and please take it away.
All right. Thanks very much for having me, and Tom. And I'll just bring up my slides here. Welcome, y'all. So I'm going to give the first half of a talk on upgrading without upsizing. And this is going to go kind of quickly. So if you have deeper questions, on the left-hand side on redwoodenergy.net's website is a free booklet. There's like a whole bunch of booklets there on how to electrify different types of buildings. They're paid for by a nonprofit in the Bay Area as part of the gas bans. And these were illustrations of how any kind of developer could accomplish all electric, including retrofits like this conversation. So there's a whole good chapter on this topic. tons of illustrations. So if this goes fast. Now, also, Tom and Dylan, one of my staff, and Tom sort of like volunteers with Red Energy. We help him out. We have a collaborative relationship. Tom doesn't technically work for us, just to be clear. But it's an honor to get to work with him. he'll let you know. He's got a distinguished career in utility management, and he's a very big thinker, you'll see. So he gave a presentation that's here on YouTube. Among others, you can find Tom out there presenting elsewhere. Just so you know, so that you can lean in and further. Quickly, I started volunteering at a demonstration house in 1995, and it was a house from 1978. It's this house up on the right-hand corner called the Campus Center for Appropriate Technology at Humboldt State University in Northern California, now Cal Poly Humboldt. I was inspired. It's like, I want to teach this. I went as a high school teacher, but I discovered like, yeah, I actually really just like I like the development part of it. Teaching is a true joy. I love this. But my calling is I think more in the doing than the teaching. So I went worked for an affordable housing development company, and we started a new division that was just based on all electric, 100% solar powered housing. So we did the first apartment complex that was successfully like net positive, more energy going into the grid than was being taken out, and all electric. And similarly, did the first housing subdivision of that, these 26 homes on the right-hand side, the little candy cane colors, Easter eggs. And then went into consulting in 2011, got laid off in the recession. So our biggest project is probably this apartment complex with like a 9-story tall solar wall in Washington, D.C. It's being built right now. They've got the foundations in. And I'm going to give like a little story time. And then we're going to go into the technology. But to understand that the core of doing an all-electric home is using a heat pump. If you're using electric resistance, then you're not taking advantage of the excess heat that's outside in the wintertime that you can pull into your house for water heating and for space heating. This technology began in about 1850 in Australia as a typesetter who got ether on his hands all the time, and it was so cold when it boiled off his hands that he thought, I wonder if I could like make ice with this process. And in fact, you can. And ever since 1850, they've been trying new liquids that boil at very low temperatures. Right now, we're mostly using liquids that boil at about negative 40 degrees Fahrenheit. But they're all like ether, a fossil fuel derivative. So on the left-hand side, you can see the first early adopters were beer manufacturers who were chilling ice, making ice to then keep their beer chilled and even ship it. Right-hand side, you can see how ice used to be delivered to people's homes. This is in World War I. And by the 1920s, people were pretty psyched about all the opportunities. And all across the country, there were 1 million microgrids set up, each home with its own big battery bank. And so, not solar, but usually either a microhydro, a wind turbine, or most commonly, of course, a gas generator. But all three of those were national by 1920s. That was in, like the Roaring 20s, things were going great. In the 1930s, not so much so, right? So one of the alphabet soup agencies created during the Great Depression before World War II was the Rural Electrification Administration. And it has some modern day parallels because in the 1930s, like 1934, when the agency starts, only 1 in 10 rural households even had electricity, whereas 9 in 10 urban households had electricity. And with electricity came like running water and light bulbs and being able to listen to the radio, which was, the internet of the day. Everything was on the radio. And getting to wash your clothes with the machine as opposed to doing it by hand. So a huge amount of money and effort went into, over the next 20 years, wiring about 60% of the landmass of our country. It was done with community co-ops. You get a loan from the federal government that turned into a grant if you did the work of laying your own wires. So people did. And by then the 1950s, there were like 1,900 utilities who banded together to start supporting electrification completely of your whole house. And they hired Ronald Reagan out of Hollywood just when he'd retired, sort of, to start a new General Electric theater, which became the #1 show in the country. Westinghouse and General Electric, #1 show on Sunday nights. and you could see every Hollywood star doing theater acts. Like they'd just get a good piece of play, and then they would have advertisements in the middle for nuclear power, and which was supposed to be the new clean energy. That was the hope is, and it is definitely a significant part of the clean energy mix of the world, but it's also proven to be the most expensive kind of energy to develop and still not have a safe place to store, and every once in a while cause some significant accidents. So in the middle, like the demonstration house that I learned from at Humboldt's campus, they built Ronald Reagan an all-electric mansion. And you can go on YouTube and find him giving tours of the house, showing off its nice new light, modern lighting and such. And of course, an electrically heated swimming pool. So the whole effort that the utilities were mounting was to try to make it so the code would require that homes be built so they could be all electric. And they succeeded at that in the 1962 code. That code was the first time that you had 100 amps that was required to be delivered to your house. And in 1962, 100 amps was enough for an all-electric home that was maybe like 1,500 square feet, which was an above average sized home. Or, yeah, like it was right at the average or a little bit above average. People are still building like 1,200, 1,300 square foot homes more as the average. Today, the average house in California is about 1,500 square feet. So 100 amps was more than enough. And the National Electrical Code, if you don't know, is the National Fire Protection Association. It's organized essentially by firefighters. The whole code is written around safety to keep it from having fires. So I want to illustrate here with real data that 100 amps is enough. So in blue, this is a line here in California in the Sacramento Municipal Utility District territory of their gas hybrid homes. This is their peak electricity draw in a year over a 15-minute period. And you can see the peak with the gas homes is in the range of like 22 amps or so for the whole house, full blast. And the peak here, this is at about 32 if you are an all-electric home. And you can see that essentially nobody is peaking past 80 amps, no matter if it's a gas hybrid home or an electric home, all electric. And these all-electric homes are older. They have electric resistance water heaters, not the heat pumps we're going to show you today, which use 1/9 as much energy. This is one other thing to illustrate, is that when you put in a cold climate heat pump, the one that you'd have to heat your house, that kind of heat pump has a computer in it, and it lowers the amount of energy in the summertime. So this is once again an illustration in Sacramento's territory, very hot in the summer, 110 degrees, you know? So this orange line, this is the pre-retrofit peak for this huge customer base they studied of 700 customers. And then they retrofitted those homes. SMUD has been an early adopter of putting heat pumps in, getting rid of the gas furnace. And you'd think that electrifying would then produce a large peak in the winter because now you're heating. So this blue line shows the peak in the wintertime in the morning when you're using the electricity to get your house warm. And you see the peak in the afternoon. But notice that this gray peak here, this is the post-retrofit air conditioning peak. See how it's lowered? Because when you use a winter-oriented heat pump, it's also a way more efficient air conditioner. So what Sacramento is saying is that they're lowering the biggest peak they have, which is the summer air conditioning peak. And their whole grid is built for that peak, the biggest of the peaks. And when they're retrofitting, they're getting lower peaks in the summertime. And in the wintertime, even the wintertime peak is lower than the summer post-retrofit air conditioning peak. This is great. They've got solutions for summer and winter. If they electrify, if they lean in, if they go that way, their grid gets healthier and better. You might be thinking that you live in a state that is against electrification. I can tell you that California is the absolute worst. It's been impossible to electrify up until the most recent code, which was only a year and a half ago. Unless you were living in a city that required that you build all electric, but otherwise the code was forcing you as best it could to put in gas hybrid. Now in green, you see states that have been embracing all electric construction because it's cheaper to build that way, adding gas infrastructure to a building that's already built all electric, because everything that burns gas has electricity delivered to it to control it, like have sparks and fans and things like that. So you build a house all electric, and then you have to add gas infrastructure if you don't have a way to cost effectively heat it in the wintertime is usually the issue. So you can see the warmer southern states, except California, have embraced all electric construction. Hawaii is at 72%, Florida is at 77% all electric construction. Colder states that haven't had access to computer controlled heat pumps, they've stayed with gas hybrid homes for longer. But gas hybrid homes, we have to understand is that their leakage is a larger climate change impact than all of the combustion related to it. You can see here where each part of the leakage, and the first biggest chunk is that extraction, a little bit of processing, a little bit that's over high pressure transmission, but then storage and also compression stations, they'll blow up on occasion, have huge leaks. So like this isn't including Aliso Canyon, which was massive, more than all the rest of that had been consumed that year. Okay, getting it to your house, that is actually a pretty significant point of leak at 0.68 leakage. That's just in like the pipes that are coming off the pipe in the street to your house. And then you see leaks at the meter because there's a pressure regulating valve, quote unquote, that's a leak valve that's designed to leak. And then each of the appliances has a 0.3 to 0.9% leak associated with it. Often even like an on-demand gas has a leak built into it. It does a puff of gas before it combusts. All this is to say that methane, which is 80 times stronger than CO2 as it comes out, the impact of it is such that about 2% total leakage is way worse than the 98% that you're burning. When you get into 3% and 4%, you're essentially close to doubling the impact of combustion. So the goal here is for you to electrify your house quickly. That's why Tom and I are here. How to electrify your house quickly without having to rewire a whole bunch of things. It's the fundamentals. In many utility territories, that first step of getting extra electricity, more than 100 amps that your house already has, it's expensive and consuming. So the time-consuming expensive part you see in red, everything that you pay for because you own. That's the weather vane, that's the socket box for the meter. It's all sorts of stuff there, wires and tubes. And then the utility, they own the blue wire that's being delivered to your house, and they own the meter. That's their thing. So what we did is a huge survey. We called hundreds of electricians in California, hundreds of homeowners, like Redwood Energy, NV5, we found is no less than $2,500. But often could be $30,000 if there's underground wires or if there's some issue with the transformer. And we found that unexpected costs and unexpected time delays happen more than half the time. So more than half the people that we interviewed were kind of pissed. So this is a comprehensive example of how you can do 2 houses on 100 amps. This we just competed with the Department of Energy, the EZ prize it was called, for how to easily electrify your house. So here you have, there's like a garage that was turned into a 700 square foot mother-in-law kind of house. It's like it's a real house. It's very cute, well insulated, etc. And then this is a double wide manufactured home from 1973. You might call it a trailer home, but it's not a trailer per se. It just got dragged here once by a semi truck, and then it's permanently put to there. So on the left-hand side, you can see that this is like divided by 2 houses. The line is in between the washing machine and the water heater here. So on the left-hand side is what we put into the small house, and it has a kitchen with countertop induction and a countertop oven, and a couple other, like an air fryer and some other countertop appliances. So it's a full-blown kitchen, and this is literally how I cook. I live in a tiny house myself, and I've got a 2-burner induction range. I've got a little oven. I've got a slow cooker. I've got an air fryer. Like, you can cook completely with just the circuits that you have in your kitchen now. But that's not the only way to do it. We're showing how to do both. It has a wall-mounted heat pump. It's 120 volt, plug it in anywhere, but it's a cold climate version, so it's like a ton of heat even when it's cold out. Has an A.O. Smith very quiet 120 volt water heater. This uses about 900 watts at peak. Has a small electric resistance element, a 900 watt element, just in case it's too cold if this is put outside. We put this in the kitchen, so it could use a little bit of the extra heat in the kitchen. It's right next to this heat pump, washer dryer. So you put the laundry in, it comes out completely dry and done in 2 hours, cleaned and dried. And then in the bigger house, this is a Ream, one of our sponsors today. Then they donated. Actually, well, A.O. Smith and Ream, they both donated to this project. So they donated their 40-gallon, 120-volt heat pump water heater that we can store at 140 Fahrenheit, has internal mixing valves, just like the A.O. Smith. So taking care of the big house, and we were using the 40-gallon Ream because we had to fit into the existing small closet in the manufactured house. Then underneath the manufactured house, there's ductwork. So we plugged into the existing ductwork, insulated it with this Mr. Cool, which comes not only with a computer to make it very efficient, but also has pre-charged refrigerant lines. So it was a little bit easier. And we didn't have to have a refrigerant technician come. It did take a few days though. It was not like an easy project to install your own heat pump, but we were able to do it ourselves. Now it balances its power demand with this induction stove. Most people don't use more than 2,000 watts, pardon me, ever for all the cooking they're doing all at once, including on Thanksgiving. But this stove has like 9,600 watts delivered to it. So we're using a neocharged circuit splitter that allows both the heat pump for the space heating system, which at peak is like 25 amps. And we're saying, okay, this 25 amp can go on the same 50 amp circuit that is delivering electricity to the stove. And the stove, which if I convert it to watts, I don't know, call it 5 amps, 10 amps, these like 5 to 10 amps, call it that, of cooking at 240 volt. These two can share the same circuit. We didn't have to do a whole bunch of rewiring or put in a new circuit dedicated to the stove. They're using both at the same time. And if they were both combined to use the entire 50 amp circuit, then the heat pump to the space heating system would shut off for 5 or 10 minutes because they were just full blasting the stove. And then the heat pump comes back on. And the house is a heat battery. I was mentioning how important it is the computers. And Brett, did you want to give me time?
Well, just real quick, Sean, I mean,
Yeah.
isn't there a way for those systems, because they can be modulating or inverter driven, that they don't have
Yeah.
to shut off? Can't they just turn down, or is that the reality that they have
Do.
to be shut off?
Well, this is under the fire safety protection thinking, which is that they're trying to make sure that this 50 amp circuit doesn't exceed its total rated like thickness of wire. Okay. If that neocharge was able to give a signal over to the heat pump to say turn down as opposed to turn off, and that is something that neocharge is making a whole home system to be able to coordinate that with the central panel to be able to do that kind of conversation. So yes, but it's pretty sophisticated getting these different manufacturers' computers to talk to each other. Like you all have problems with our routers and our headphones, and it goes on and on. So don't assume that's a simple thing. But yes, absolutely, you could have a stove and the neocharge, which you're trying to do, be able to talk with the central computer and tell the heat pump turn down a little bit, and then everything be cool or warm.
Thank you.
Yeah. And here's what that computer looks like. I mean, this is nothing fancier than what you have in a handheld calculator that is saying what temperature outside, what temperature inside, how fast do I run the fan inside of this, how fast do I run the compressor. That takes like you guys ever had a single speed bicycle when you were a kid? It has one gear. And then you had the first time when you had like 2 gears or 6 gears or 12 gears, like you got a fancier bike. This is the equivalent of taking a single speed heat pump, which means the fan just goes at one speed, the compressor's at one speed. That's the old fashioned type, single speed, and turning it into like a 26 speed or a 100 speed, something that takes you up and down the Tour de France Alpine mountains kind of situation. That's what the computer does. And so you can constantly get the fan and the compressor working at the right speed for the temperature inside and outside. That's what it does. It makes it way more efficient, way quieter, because it allows you mostly to be running everything at a lower than full blast. And it allows it to then just sort of stay on as opposed to having to turn on and off. A lot of people don't like the sound of a furnace turning on and off in their house when they're warming the house in the wintertime. And this doesn't do that. This is just a low speed of fan and doesn't wake you up at night with the whole big noise experience. And I just point out, this is around reducing power demand. So this is, you put a computer in, And ideally, you put wall-mounted fan coils or floor-mounted fan coils just because it uses less power. If we're talking about how to save power in a house, the ductwork has a lot of friction in it. And you have to have a powerful fan to blow full blast. And each of these systems, they don't have friction. There's no ductwork there. And so the fan doesn't have to blow as hard. And you're frequently keeping rooms at different temperatures and it's not ever full blasting the whole house. So a lot of efficiency options here to reduce the total power demand of space heating and cooling. Here's the water heaters. I mentioned how like an electric resistance water heater uses 4,500 watts. This Ream here, our sponsor, 500 watts. The A.O. Smith here on the left, 900 watts. And if you have a really big bathtub, if you're like the sitting tub kind of person, 100, 150 gallon bathtub, then you have enough money to get the right sized water heater, which is this one here, like the Sanko. And this is for sitting tubs in Japan. And this is all over the United States. It's like 2014. And it uses CO2 refrigerant. And even though it's producing almost 4 times as much hot water potentially, it's still only 900 watts total of power. So these are different efficient, using the same amount of energy roughly. But the CO2 one is different, using a fancier refrigerant. It's got a bigger fan that you can see there. It does more heating work. Here's your washing machines. All these are 120 volt, plug right in. So the left-hand side, this is a condensing washer dryer. This is what I have. It's essentially a glorified type of electric resistance. And it takes like 3 to 4 hours to do from dirty laundry to completely dry and clean. Upscaling yourself, if you'd like, is you can now get the heat pump version where it has, this is just a dryer, but it dries very fast, 7.8 cubic feet. And this is the combined one at 5 cubic feet, which is still a lot of laundry. And this, so like in just 2 hours, you can put in your laundry that's dirty and it comes out clean and dry, and uses half as much or a third as much as electricity as electric resistance and less power. Here's like the Neo charges on the left-hand side. I just showed you that one in that example house or the example 2 houses that we did on 100 amps. Here's other products. Simple Switch, which I think is out of Ohio. They're an excellent product because they don't have a computer inside. And so some building departments like San Francisco's, they don't want a Neo charge with a computer in it. They want something that's a traditional transfer switch. And essentially all of these are functioning as fancy transfer switches with or without a computer in them for managing different amounts of larger or smaller amounts of power, like fast EV chargers versus not. Almost done here. I'm going to hand it off to Tom. This is next scale up. This is not like something you plug into a single 240 volt outlet, which shares between 240 volt appliances. That's just a simple transfer switch. This is a whole smart circuit breaker panel. So on the left-hand side, this is 100 amps that can plug in up to 400 amps of stuff. On the right-hand side, this is a smaller version, costs less, the Lumen, and this can take, they do 60 amps, and they take it up to 180 amps worth of stuff. One sec, my mom is dropping off some baked goods here because it's morning. One moment. Oh, thank you. World, these things you can plug in up to 400 amps of stuff on the one on the left, right? And the one on the right is like 160 amps, 180 amps of stuff. And on a rare possible occasion when you actually went past the limit that you have, say 60 amps or 100 amps, then one thing would turn off. Maybe it's your swimming pool heat pump. So here is the connector. Utilities have to approve this, unfortunately, but lots of utilities have. And this allows you to plug in a solar array up to 15 kW. Usually a 100 amp service and panel can handle about 4 kW solar on the roof. The average solar array is like 4 to 5, so that's okay. But then if you connect the solar array in at the utility meter, you can do up to 15 kW, which is a huge, huge solar array for like a big old mansion. So just showing how there's some options out there for where you plug stuff in and how it gets worked out. And that's it. That's my presentation. I want to make sure Tom has a chance, and you've probably been over there. Yeah, exactly. I'm going to go get that cinnamon roll as soon as I turn off the camera.
Hey, hey, thanks so much, Sean. And yeah, yay, mom. That was
Yeah,
so
yeah,
so
Mom.
nice. She was able to bring that in. I I did see a question in the chat too, but just thought while you were on the topic of those splitters, you showed in that array a bunch of them that were
Nice.
on the order of $400 or so. This is one I got from a place called Electron, is their name, and it was about $190. And so it's got one plug that plugs in. They make a 30 amp version and a 50 amp version. This is the 50. And then there'd be one of the dominant plugs that would be on any time it wants power, it gets power. And when it's not drawing, the other plug has access to the power. And so that's how things take turns in those circuit sharing devices. And that's just one of the control strategies we talk about. But Sean, you've taken us on a great journey about the history of electrification, some of the benefits, some of the problems with gas. And then one of the questions I thought you might answer in the chat was a participant was asking about have there been any all ductless installations on, I believe it was multifamily, kind of many units.
Yeah, let me show you. So the most common type of HVAC system, HVAC standing for heating, ventilation, and air conditioning. So the most common type I have is ductless. And the product that people are using, there it is this here. It's the really popular one because it's the least expensive per room. And a ductless system usually put one fan coil on the wall per bedroom and in the living room. That's like the way to comply with the code and make everyone comfortable, etc. So this is a type of heat pump that sits on the wall, and then you cut
Mhm.
two duct holes through the wall. It fits in between stud
And,
bays. So
and
it's
Sean's
good
cursor is on
for,
the far left, showing that
yeah,
a Epoca unit that is
yeah,
a packaged unit.
that's the one. And they do about up to about 15,000 BTUs, so 1.3 tons per heat pump. You just plug them into the outlet on the wall. They can also come with ERVs if you added like $1,000 or $2 to them. It's not cheap, but ERVs come with them if you'd like. They can also have like condensate evaporators so that the condensate doesn't have to be plumbed somewhere, but can just be blown out. So it's helpful for retrofits. So this is we found this to be $3,800 per room, and ductless mini splits installed for about $5,000 per room. So it's generally proven to be less expensive than putting one of these compressors up on the roof, running tubes down through the walls, and then putting these fan coils on. And these things, these Afocas, they're actually pronounced in it's Italian Afoca, but I'm like from Wisconsin, so I can't quite pull it off. So these Afocas, they're like got awards from the city of New York because they have that huge amount of multifamily housing in New York. So this is like one of the premier products for doing retrofits, electrification style.
Um, Two quick questions. I mean, is taking that approach versus a ducted system going to be make it easier for you to take this kind of watt diet approach?
Mm-hmm.
Yeah,
Um,
yeah. While Sean choose, I have an answer there. Yeah, I put a little thing in the chat. I've noticed from doing the thermal calculations that duct work loses a whole lot of heat, and when people are putting duct work in their attics, for example, they're having to size up their heat pumps another half ton or three-quarter ton just to handle the heat loss in the ducts before it gets to the registers. So something has to power that extra heat pump, and so yeah, we do see that by going to ductless mini split types or to these packaged terminal units like in the lower left, both of those can avoid the duct work, and that can then decrease the total power content
Yeah.
needed in the house.
Now, here at the GreenHome Institute, we talk holistically. I know you all do too. So not just energy savings, but health. And I understand correctly with some of these mini splits, there's concerns about humidity control, and being able to control it and get it out. So are then the trade-offs of having to bring in some sort of dehumidification system, which would then put an increased power load. Now, if you're talking about that, how would that factor in?
Yep. what I see is that they handle dehumidification just fine. That the one thing that central systems can do noticeably better than a lot of these little units is air filtration. So
Right.
filtering out any small particulate matter from the
Sure.
household air. So that's a place where central systems have a built-in advantage if you build in the big MERV 13 air filters and the
Yeah.
fan power to handle that. Otherwise, you can get little standalone air filters that run in your house on whatever schedule you want that are
Right.
continuously cleaning the air. So there are ways to do that and just plug those into regular outlets. And like Sean had shown in the other graph, the panels actually are not overloaded because equipment has been getting a lot more efficient and lighting's been getting a lot more efficient. We've been shrinking our our power uses. We've been adding new ones, but shrinking the others. So there's room to do air filtration, definitely.
Sure. Well,
And
go ahead and continue on, and then we'll get to some more questions. So thanks, Tom.
there's a whole bunch mess of them. I'm going to try to handle them in the chat there. One person is asking about for new construction apartments, Eric Wheeler and others, this can you please repeat the cost of the AFOCA compared to a ductless install? Okay, so the AFOCAs on apartment complexes, they purchase for about $2,000 to $2,200 a piece. You might be buying 50 or 150. You buy them in bulk. That's their cost in bulk. Then, because there isn't a refrigerant line to set, you save some cost because a carpenter can install an AFOCA. They just have to have it leveled. They have to be able to plug it in into the ductwork. But carpenters can do these packaged heat pump installations, and that's also true for other kinds of packaged heat pumps, like the through wall type, like that might make from Amana and such. It's just those are, well, they have issues with the shear wall. They cut a hole in the shear wall. They have other issues. They're usually not as quiet, etc. This is my favorite because it doesn't make the architect so upset with having big holes in the wall. It just has small ducts that you can kind of hide. So $3,800 is the full installed cost per room for an EFOCA. And ductless mini splits we've found are $5,000. And this is, I'm working with a very large GC that does this pricing, and it's been priced out over and over by other companies who haven't told me how much, but they've said the AFOCA is less expensive. So some people would say it's right at the edge. Like if you get 3 or 4 bedrooms, maybe it's less expensive to do a ductless mini split. Other developers like, no, you should just do AFOCA the whole way. So anyway, that's the answer. And I want to make sure Tom has a chance to do his thing. So I'll just put my comments in the Q&A and take it away, Tom.
All right, thanks, Sean. Let me get this thing going. All right. And so thanks, everyone. I just want to share with you a few quick ideas and a little more detail on this power efficient design or the Watt diet. We just call it different names, but it's all the same thing. We're basically trying to get all of your end use needs met in the more power efficient ways so that you don't have to upsize branch circuits in your homes. You don't have to upsize the electric panel. The utility doesn't have to upsize that service wire. They don't have to upsize the transformers in your neighborhood, and things can move a lot faster. The basic idea is, we my partners and I partner with a lot of different great people, including Sean and the Redwood Energy team. But in some of the other studies, we've gone out and done these power efficient designs on a number of homes. And we started kind of in a nebulous way where anything can happen. But I want to share with you an idea for doing this planning where you just start at the full power efficient end of the spectrum in all 5 of the end uses, in the space heat, the water heat, the drying, the cooking, and the car charging, starting at the power efficient end of the spectrum and then seeing if the client wants to move into more power intense things. Because really what we all want is our needs met. We want the cold beer and warm showers. We don't want amps. I've touched amps before. They're not good for you. They hurt. So we really want to focus on what we want. So then, what I help people do is try to mention the merits of a power efficient plan and help your client understand what they're really out there to get. And helping them get that and get a faster install with least labor install. And that frees up more labor force to do the neighbors, because if we're going to save my daughter's future, we're going to have everyone electrify. It's not just a few of us. So we need to be working on how do we make less pressure on the workforce, less pressure on the utility distribution system, so things can happen faster and they don't get shut down early. All right, so we start with the most power efficient plan and labor efficient plan, and then we help the customer identify if they really want to move off of that. One of the graphs, I love my little nerdy graphs. This one is showing the 5 basic end uses. Towards the top, you see clothes drying. So those 5 bars in there, and there's a 0 bar that you can't see on the very top one, that one and done washer dryer combined unit that Sean was pointing out earlier. That thing washes and dries the clothes. Imagine if you had a dishwasher and a dish dryer machine right next to it, and you had to always take the wet dishes out of the dishwasher and move them to the dish dryer. A lot of people do laundry that way now. They actually take wet clothes out of a washer and move them to a dryer. These new one and done machines handle both tasks. They don't fold the clothes yet, but they do wash them and dry them. And then you just come back 2 hours later, and it's now down to 2 hours with the heat pump versions. They are nice and dry. So anyway, I love those machines. And then I showed now the power intensity, and that's what the scale at the bottom of that graph is from 0 to 12,000 watts counted on the panel of all these different devices. And so in each of these 5 end uses, I'm showing power intensity. And so at the resistance dryer level, you see it counts as almost up to 2,000 watts, but that's counting it at 40%. And that's what we call a coincidence factor, because the real dryer is pulling 4,600 watts when it's drying, but it's only assumed by the electrical code to be 40% likely to be on during the time of the whole building peak. So the electric code allows these certain coincidence factors. They call them demand factors, but that word doesn't ring a bell for me, so I treat them in utility speak. It's how coincident they are with the peak. Anyway, that's how to read this chart. You can see the top one. Then the middle section's about cooking, and there's a new battery range out that can plug into the 120-volt circuit and charge up its 3 or 4 kilowatt hour battery over the day, and then use both the circuit and the battery to do high power cooking when you want to cook. And then we've got more conventional cooking ways down there, and Sean showed you even the countertop methods that go on 120-volt circuits. The middle section's about the water heaters. You see the little tiny bar for that 120-volt plug in the wall heat pump water heater. That's what the HPWH means. And then the big bar at the bottom, counting almost 2,000 watts, is the most prevalent 30 amp version of heat pump water heaters that are hybrids. They still have those big 4,500 watt resistor elements in them. I don't like those. They take up too much power intensity on the panel. And so I want to leave that space for other things that are more important to me, because I really don't care how long my big tank water heater takes to reheat itself. I do not care. What I care about is we get all the hot showers we want when we want them. And that we do with a bigger tank and a mixing valve. So we've got ways to meet our needs. And then I do not fixate on bird dogging my water heater to see that it's doing its job while I'm off at work. So then next chart down is just comparing 2 different 3-ton heat pumps, a more power efficient one and a less power efficient one. Takes up more power and has a lot of people prescribe these resistance backup strips. They have a lot of power intensity. I'm out here in California. Our climates are gentle. These new inverter-driven heat pumps are plenty powerful to meet our needs with no resistance. And that's the way it is in a lot of the country. But talk with your local pros, the ones who are really educated about this, and not the ones going on old information from the 1950s when heat pumps always needed resistor backups. But get modern information when you're getting a heat pump. Things are changing fast and they're getting better fast. The bottom chart there, bottom section, is just different ways to get different amounts of mileage per year or mileage per day out of your different circuits for EV charging. That top small bar up there is for just plugging into a regular 120-volt circuit. If you did that 8 hours a night, you could be getting 13,000 miles a year. That's about what most people drive. Their electric cars, they may not do all that charging at home, though, so you might even need less than that much home charging. But one of the sweet spots I see is just using a 20 amp breaker and a 20 amp setting on an EV charger is able to give you 39,000 miles a year. And you could future-proof that system by putting in the stout 50 amp wire in case you ever change your mind and want to go up to one of these behemoth car chargers and play Indy 500 at home and things like that. But that interferes with your neighbors being able to electrify. Okay, so that was my kind of nerdy version of the graph. Then this is more gamifying it. And so what to look at in this chart, it's the same thing. There's 5 end uses. The 4 on the fixed to the house are set into the corners. You can see drying, cooking, space heat, water heat. And then just how power intense they are kind of extends down in and squeezes what's left over for car charging. And whether you choose less power intense ways to meet your end use needs, you're leaving more space for car charging or more space for letting the neighbors electrify. But that's just kind of maybe the board game we can make it sometime for how to do power efficient design. Right. And let people understand how much of their end use need can be met by these different devices. These new 5 cubic foot drum combo heat pump washer dryers, they're available now from GE, from LG, and from Samsung. So 3 big companies are making these great 5 cubic foot big drum combo heat pump washer dryers. And so if you want to do laundry all day and just only visit it 6 times instead of 12 times if you had the 2 machines and you're always transferring wet clothes around, you can still do 30 cubic feet or 120 pounds of laundry washed in that day. You can get 5 showers out of 74 gallons of hot water. That's a first hour rating on a typical 50-gallon heat pump water heater. But you can look up these first hour ratings. That's what to pay attention to in these water heaters. And you can put thermostatic mixing valves on the water heater plumbing so that you can supercharge the water heater, say to 135 Fahrenheit. Though this thermostatic mixing valve mixes that down with some cold water down to even more gallons of 120-degree water that you further mix down in your showers, typically to 110 is where a lot of us like it. And so you're showering, you're getting a lot of showering. These heat pumps I've been talking about give you year-round comfort at 70 to 72 Fahrenheit. Pick your favorite seasonal temperature. You just leave them on longer. That's how you get more comfort out of your heat pumps. And then you can always retrofit your home after you put in the heat pump. You do not have to delay heat pumping your home while you retrofit it. That's a mental construct upstairs. If we've already waited a decade or more to upgrade the home insulation, why put the heat pump after that thing? Why not do the heat pumping now, electrify now, and fine tune your insulation as you eventually get around to it? Anyway, we do like those induction cooking. It gives us safer burners, and that's a big plus for us as end users, and good clean air quality in the kitchen. And we do love our charging. Oops. And, we can just compare costs. There's a lot of cost savings here in the middle column of going to power efficient devices and not having to upsize circuits, and help people understand if they're going to stay on gas, they're going to face gas device costs anyway. These replacing your gas devices when they burn out is not free either. People need to not keep looking at it like it's free. 2 last slides here. There are 7 basic ways to lower your amperage requirements on your electric panel. You can pick the higher efficiency equipment, these heat pumps with better COPs, with better coefficients of performance or heating season performance factors going up above 10. The more efficient it is, the less power it needs to get its job done. You can pick power efficient versions of the water heater, the dryer, the cooking, etc. And then avoid oversizing the heat pump. It is so tempting. And there's a split incentive where the contractor wants to oversize the unit for two reasons. One is they're marking up the unit. And so the bigger the unit they can sell you, the more markup they can get. And the other is they're thinking you won't know how to run it and you might complain if it's a slower than a rocket gas heating system on recovery. And so they're wanting to decrease the possibility that they get called because you are unsatisfied because you're trying to use deep nighttime setbacks and then catch up in 1 hour in the morning. These heat pumps maybe need 2 or 3 hours to catch up with your morning targets. So don't set them down so low at night. Okay, and then to avoid oversizing the car chargers, I've already said, pick multifunction devices like the combo washer dryer and the combined cooking range that's got the oven and the burners in it. Those machines already have power control built into them. They've got more burner watts and then they have connection capability. So they're already doing internal controls. And then when you've done all that power efficiency stuff and considered that building shell improvements, then I get to where I'm considering in-home controls like the circuit sharer. And here's a version of a hardwired circuit pauser with a breaker. And then this thing's got a couple of these little CT clamps to measure the current, and it goes on the panel and it can pause one of the circuits, like the car charging circuit, if the panel ever got to 80% loaded. So I can do that kind of stuff. Or there's the big overkill method of buying the full controlled smart panel that can control every circuit. But I found you really only need one or two circuits to control, and you're probably good, unless you're going to fit a whole apartment building onto a panel. Maybe then you'd want to control them all. All right, and yeah, decrease your loads, get around to that air sealing, the insulation, etc. I do not place that ahead of electrification. I just let you do it whenever you want. I think, oh yeah, oh, one, so that was the 7 ways to free up ampacity or capacity of the panel. There's also 11 ways to free up physical space, because the other function, the other thing we're working with is people look at a panel and they think it's full. And so there are ways you can deal with freeing up the physical space. You can pick these multifunction appliances like that combo washer dryer frees up 2 poles that used to go to the electric 240-volt electric dryer. Frees up those 2 poles. They can now go either to a sub panel or to the car charger or something else. And so they can then be used. You can free up the furnace circuit by picking these heat pumps like the Efoca that Sean was picking. That doesn't need a separate furnace circuit like most gas-fired homes have. And then even if you're using a mini split system, either central or ductless, both of them from the Japanese makers in particular, I know they have an umbilical power cord coming in from the outside unit that powers the air handler in the building. So it can power that thing that looks like a furnace that's now just an air handler, but it's not on a separate circuit. It doesn't have to be. It's on the same circuit powered by the outdoor machine. Okay, then you can use tandem or slim breakers. And so that's what this breaker is. It's just the same width as a normal breaker, but it's got 2 different branches coming off of it. That frees up physical space. There's also things you can do, since we're now underloading so many of our lighting circuits. You can pigtail 2 lighting circuits that are underloaded together and put them into one junction on a breaker. And they also make these little WIGO clamps to do that same type of pigtailing. So there's different ways to combine circuits and bring down the number of circuits needed and freeing up circuit spaces. There are even some GE brand breakers that have a special clamp that can hold 2 wires. And you can, instead of using a pigtail, you can clamp both of the now combined circuits into the same thing. But do pay attention to what your electrician says. I don't want to go over the amperage issues there, but do that in a safe way. And there's other ways to do this too. There's junction boxes that you can put out in your building elsewhere to bring 2 circuits together and bring the 1 wire in. And you can also add sub panels if you want. And so a sub panel is not too expensive to add. It is just a new breaker box off of one 2-pole feed going to it that can serve a number of circuits. One of the opportunities to do that is if you have an old air conditioner line going to your air conditioner, that thing is often oversized at say 50 amps, and you can then put in a sub panel that can serve several loads off of that. And then Sean showed you that connector, which is a way to line tap the solar feed back in behind the meter instead of using breaker spaces. And well, actually, he showed you connector, the meter collar, but old school solar installers also know how to line tap solar, which is electrically accomplishes the same thing. And that's all I have. So I'll stop sharing and see if there's any questions.
Yeah. Tom, Sean, I forgot to ask at the beginning of this, do you have time to stick around a little longer for some more questions?
Yes.
Yes.
All right. Well, let me know if you have to get going. Otherwise, we'll keep having a conversation for a little while. Real
Can I
quick.
share my screen real quick with folks?
I got one thing to go through, and then I'll let you do
Okay.
that. So, real quick, everybody, we're wrapping up so if you've been here for the whole hour, you are CU approved, but we're going to keep going on with some more questions. So we'd love for you to stick around. And as those questions are coming in, a big reminder that yes, this session is being recorded. It'll be posted on our YouTube channel in the next couple of days. You can go over there and look then, or you can go there now, hit subscribe. You'll get an instant update when the session is available to watch, and hopefully share with friends and colleagues. For those of you listening to this in the future, not right now, but on demand, the recording, you need to take your quiz with an 80% passing rate, and you will receive your continuing ed certificates. For those of you here today that's been here for the CU hour, make sure you have the name on your Zoom that you want written on your certificate. You'll check your inbox for certs at gutenbergcerts.com. It's probably going to go to your spam, so check there, and you'll receive your certificate in the next couple days. Take that survey that pops up. If you're AIA, we need your numbers in there, but either way, take that survey that pops up, and we want to hear your feedback. And as those questions are coming in, again, a huge thanks to our board of directors, our volunteers, our executive director, Jose, Reina, our over 350 members who are supporting us to allow us to keep doing these sessions, and our top tier sponsors, such as like Rheem, who are putting out products there to help make it easier to electrify, build Equinox for smarter ventilation, Panasonic, all of them to allow us to do what we do. So yeah, Sean, go ahead and click share on your screen there, and it sounds like you got a thought to share.
Yeah, well, there was one of the questions that came in, I think, from Fletcher Otwell, who's a rural contractor committed to installing heat pumps. He wanted resources. So
yeah, and I was hoping that we could actually go through this a little bit if you have it and you
yeah,
want to show people how to use it. I was hoping that we could do that. So yeah.
so the watt diet calculator, this is a web page that Red Energy hosts, and Tom Kabat, this fine man here, he created an Excel spreadsheet. So at the bottom of this page, first is like a cute little video from Disney that they made about the watt diet back in 1945. Some examples and illustrations, like for electricians, you can give them this example panel and say like, hey, this is what it would look like to have a 100 amp household if it was, in this case, a 2,000 square foot house. It's an example. Here's one for 3,000 square foot house. You know, like different strategies, the circuit shares. And then at the bottom, you have a screen capture saying this is what the watt diet looks like. And there's an actual downloadable Excel spreadsheet that has the whole National Electrical Code built into it. And I'm going to hit download. And then I'm going to open my downloads and share with you my screen. So new share. This is big. Get it. It's got a cover sheet. It tells you stuff. This is for someone who's a technically oriented person. Not gonna lie, you know, like you should the first thing you're going to do is you're going to fill out the amount of heat that your house needs, because that size is the heat pump, and that is a really key part of the whole design of your like power demand. So there's yellow enterable information about your house. So after you've done that, you can, the next one here is choosing the heat pump. Figuring out what is going to be the power demand of your heat pump. And there's some illustrations of the BTU loads versus outdoor temperature. Then this one, the next sheet in, let's see here. I'm trying to just zoom it in so it's easy for us all to see. Okay. Then we start getting into the laundry machine, the kitchen appliances, the water heater, etc. If there's an EV charger, things for you to choose. And there's information at the end about the products that are available out there. So we have like a whole bunch of just options for people to look at. But at the end of it, on tab 3, the watt diet and panel sizing, you'll have the amount of allowed watts, your minimum panel size for these things. It gives you some readouts on what is the power demand according to the code. This is one way of doing it. Another way of doing it is to study your actual existing peak power demand in a year, and then add a safety factor, I think of 25% to that peak, and then the rest of the power that's available to you, you can start electrifying with. So the upshot of it is that, like I said, this is way too fast. This is not a training. Instead, you would download this and spend some time with it. And then there's also like our little booklet that's a free download that explains it in more detail, but it's more or less like what you saw today. Okay. Then there's other questions. I'll stop sharing this.
Yeah. Sean, I see one question
asking
if the watt diet calculator is appropriate for multifamily buildings. And you and I have done some multifamily consulting work on it before. The version I think we've set up in that downloadable spreadsheet is specifically for single family. There are a couple little other sections of the code. I do mention this NEC Article 22083B. That's the one we're using in the calculations. There are a couple other code sections that are usable in multifamily.
And we have a multifamily calculator that's not posted. Mm-hmm. So if anyone wants to contact me, Sean Armstrong, let's see if I'm putting it into the chat right now, Sean Armstrong PM at gmail.com. And I'll put you in touch, with Gary Goslin, who's an electrician on our team, and he's the one who's managing our multifamily. By the way, other people have mentioned multifamily. It's important to know that multifamily housing does not have a limit, does not have a 100 amp requirement. Instead, it's really whatever the electrical engineer says it is. So I've seen as little as 30 amps, which is rare, to be given to an apartment, and usually 60 amps or 80 amps. And what we've found is that you can do an all-electric apartment if you have 60 amps. You have to do all the power efficiency we're talking about in a standard stove. So 60 amps is a bit of a threshold unless you start addressing the stove in the kitchen. That's usually the biggest problem because it requires a 50 amp circuit, and you can't have a service that's the same size or smaller than the largest circuit. So 60 amps is kind of the threshold before you start having to think of something more creative about the stove. And you're welcome, everybody. Let's see, looking for other questions. Q&A.
John,
go ahead.
One question that came in, and you probably answered it, but just to bring it up, is there was about, and I'm just going to expand on the question, but, again, obviously we wouldn't ever want to tell someone, hey, in order to meet your watt diet or your energy goals. And actually this is the same problem that happens in energy modeling, right? So if you're trying to meet your energy efficiency goals and you start adding ventilation to your project, what happens? Your energy efficiency becomes worse, comparing it to no ventilation, right? And I would assume the same case here. Now you have to add this extra power load. So the question is, are they making any systems that are going to be more friendly with ventilations, whether they be bath fans or supply or energy recovery ventilators that you're seeing out there?
Well, let me flip it a little bit because what we've found is that energy recovery ventilators, which address otherwise unbalanced homes with leakage, but basically they are recovering air conditioning as it's going out and getting cooler air brought in, or in the wintertime, they're recapturing heat as you're exhausting air out. That reduces the HVAC load, the air conditioner load or the heating load, and it reduces it in a power efficient way, such that, like an example, in a commercial building,
Hmm.
old commercial building might have 40 tons of air conditioner heat pump up on the roof. And you might put in then 20 tons as your finished retrofit, plus the equivalent essentially of 20 tons of ERV. And the ERV is going to use far less power than a potential other 20 tons of heat pump that you could have put in there. So in that way, that's commercial buildings frequently don't have to have any kind of service upgrade if they install ventilation, energy recovery ventilation, that then allows them to put in a much smaller set of heat pumps, and it frees up power capacity for other things.
Yep.
So I think ventilation, if it's balanced ERV, HRV style ventilation, is actually a power savings device.
Yep. Yeah, I definitely agree. Think of it like you're adding a COP 20 HRV, so it's got this excellent coefficient of performance, saving 20 times its energy consumption. And then that's letting you put in less COP 3 or 4 heat pump.
Mhm.
And so that's where we're really going to save the watts. We invert those COPs and they show up as watts.
And again, we're talking comparing it to something that had an exhaust or supply only, because if you're comparing it to nothing,
Right.
then you're talking about something that increases the load. I mean,
Right.
there's no way
Yeah,
around
you
that,
are
right?
doing more service in the building. You're
Right.
providing fresh air, and
Yeah.
if that's a new thing to your building,
Yeah.
it does take some power and energy to
Yeah.
condition that fresh air if that's what you're increasing.
But if the fresh air is being delivered with an ERV or an HRV, then that can lower your HVAC load overall and still reduce the total power demand. So if we're to take an unventilated apartment complex and, well, unventilated is a weird one. We don't have a bathroom fan. We don't have,
Right.
we just
It
don't have,
does happen, right? I mean, but is it
right.
legal? I mean, I guess that depends on the state and the
And
city.
right, and how long
Old
will the
buildings.
building last too with all that moisture
Right.
buildup?
Right. But
Ugh.
we see it all the time. So here's a question that came in, and there's a interest in DC, right? Instead of AC. People claim it can be more efficient. We don't see it too often, but so the question is kind of how does that approach interact with this approach?
Ooh. So I learned a lot from people's presentations on DC, and I've lived in a DC wired house. That demonstration house that ran on batteries off grid and had a whole DC circuit.
Yeah.
Caused actual real complications with plugging the wrong device into the wrong outlet, blew up like an inverter. Really expensive to have hybrid wiring.
All right.
What I learned from all these presentations of DC enthusiasts was they were essentially saying we need to rewire the house with DC in order to accomplish our goal. And what I know is that apartments can't get rewired. And frequently houses have real challenges with rewiring, but
Right.
rewiring apartments means at best surface mounted conduit that you're running around through hallways and through cabinets and things like that.
Yeah.
But instead, so what I learned from the DC folks was like rewiring is the real challenge. And what I learned from appropriate technology education, like that was that demonstration house, is that we should carefully look at what's there now and
Uh-huh.
adapt things. And so I've been very like philosophically trained in thinking like, no, we're not going to rewire a house no matter how efficient that is. We're going to use the existing wiring because that is the complicated, limited resources wiring the building.
Right.
Use the existing wiring, and we're going to put all of our efficiency at the heat pump itself, even though it's a DC heat pump, even though it hypothetically could be wired DC.
Yeah.
It's not going to get wired DC in apartments. It's probably not going to get wired AC in apartments. It's just purely going to be the wiring you have now because you have lead paint and you have asbestos drywall and you have people living in the place. And
Right.
that's actual real world that we live in.
Right.
So, yeah, I think the DC wiring is going to be limited to low voltage lighting for quite a while, and it's not going to get incorporated into appliances, computers, HVAC systems, or domestic hot water in the near future. And if anything, I would say it's a delay.
Mhm.
Like we really time to rewire. Tom and I are very oriented on the amount of time that we have
Yeah.
left to not completely melt our glaciers or not have whole, large systemic changes.
Right.
How much time do we have left?
Right. We're basically figuring out how do we accelerate the transition, and then
Yeah.
purists wanting to keep everything in one voltage format. Go ahead, purists, go there, build your new stuff. We're busy. We're trying to save a climate.
No offense intended, right? Like we're all
Yeah.
enthusiasts, but our particular brand is like, how do we electrify faster with a lower budget in a way that people still feels comfortable, pleasant, the good life,
Yeah.
So that's our very, Tom and I have been working together for, are we 6 years now? 7 years of talking?
Yep.
Like we are oriented together in what we're trying to do.
Yeah. Um, you mentioned some strategies for the water heater. So larger tank, mixing valve. Now, what about, does this bring in a win for water conservation,
Yes.
and so again, having low flow shower heads, low flow aerators,
Yes.
you're saving
Excellent.
water, but does that then also show up in your calculator as a way to reduce your,
I have not really worked on the plumbing side of the calculator, so the calculator when it gets to water heating is not super sophisticated,
sure.
I think DOE's got some things in their new heat pump water heater calculator that maybe can let you
Yeah.
go after the efficiency. And then there's one more thing. As an energy nerd, I have a cover over the top of my shower stall that holds the steam in.
Mm.
And so I get these wonderful steamy showers, and I can turn the water off. The the mythical
Huh.
Navy shower where you turn the water off in the middle of it and soap up, and I save those 6 or 8 gallons of hot
Sure.
water usage too. And yeah, we can get a lot of showers per tank of water by doing what you're saying, better efficiency shower heads. And what I'm saying, go ahead
Mm.
and put a plastic cover over the top of the shower stall and save your bathroom walls.
Right.
My bathroom never gets condensate anymore. All the moisture stays in where I want it with me in the shower.
Our water heaters, we've focused on the efficiency of their. So basically, a 40-gallon water heater and an 80-gallon water heater use the same amount of wattage. They
Yeah.
both have 500-watt compressors. So having a low flow shower head means you get an extra couple showers. If you go from a 2.5 to a 1.5, and 1.5 is a fantastic shower, and I've been showering that way forever, and it's not a
Yeah.
sacrifice. It's a great shower. I have long hair. It's a great shower.
Yeah.
The the wattage demand in terms of this conversation, the peak wattage demand, it doesn't really make a difference. The low flow shower heads, what they're going to do is make that 500-watt compressor turn on sooner and run longer.
Sure.
But it's not
It
really a
wouldn't
power
really.
savings to put in low flow or shower head.
Right. But they can get people over that anxiety where they might have thought they needed 4,500-watt resistors to extend the life of their 60-gallon tank,
Yeah.
and or extend
Yeah.
the delivery of their 60-gallon tank to meet the needs of more in-laws.
Yeah.
But
Yeah.
having a low flow shower head, now you're ready to meet the needs of all your guests.
Yeah. Now, obviously, the point of this is how can we rapidly electrify, right? So
Yeah.
taking that, all right, ground source heat pumps, right? It doesn't really speak to doing things quickly and costly. Now, of course, there's the Inflation Reduction Act tax credits. A lot of people forget now there's 30% back for those, up to 50% in certain situations, like for nonprofits in low income areas. But
Ground source heat pumps are like really important in the central part of Canada and northern Alaska.
okay.
Air source heat pumps, these big old fans, that's all you need up until central Canada, like a computer with a big old fan.
Okay.
And of course the right refrigerant and such. But yeah, like the Mitsubishi Hi2s, the Carriers,
Yeah.
like a
You're
whole
not going to
bunch
get
of
the lower startup with a ground source heat pump. Like it's that, it just seems like, and maybe I missed part of it. It's that startup is just, I see it. It's the worst.
Well, Tom, why don't you speak to the kick-in startup voltage surge that I think that Brett's speaking to? You're the mechanical engineer.
Oh, sorry, I missed that.
Well, so the question is I'm saying, do these ground source heat pumps have lower startups, lower kick-ins, because I see
Oh,
those on
the
the air
yeah.
source. I see the startup. It's, it can be high, especially in
Well,
the
on
winter.
inverter-driven machines, when I've got my meter on my inverter-driven mini split air source, the startup's nice and low. So the inverter-driven machines have a low startup. They're converting AC to DC. They're not having this big power surge that people associate with AC machines kicking on a single speed model, that big loud bang of your neighbor's air conditioner turning on. They
Right.
don't have that. So yeah. So I don't see really a difference in the ground source versus air source. Once you've gone up to inverter-driven machines, then everything's fine.
Sure.
Bradley in the chat asked something about uh, about teenagers. My solution to teenagers is, hey, maybe you do want a smaller tank. Let the teenager learn about the limits to growth or something. But and then set your alarm so you take your shower before them. There's no reason they need all that hot water.
I have a 35 gallon heat pump, no, sorry, 30-gallon heat pump water heater is given to me. And I put a low flow shower head on it, 1.5, so great shower. And then I have my tenant who's living in this tiny house with this 30-gallon water heater. How long could he stay in the shower? And for 35 minutes, he still hadn't run out of hot water. So if that's true with a 30-gallon tank, and the heat pump, of course, is running, but it wasn't electric resistance, is one of these like 500-watt compressors, I think it's a little bit overblown. We have the largest study of water heaters in our country, of people actually using them, second by second, monitoring many, many dozens of households. What we found is that it's only 7-person households that run out of hot water. And it's usually like on a Saturday. But if we have an 80-gallon tank, which is the largest of those varieties, we can do just like anyone else, like 4, 5, 6. And then 7 is its whole thing. Like you should have one of those big Sandin ones I was showing you with a big fan. That's what happens if you're like a family that's had lots of children, or multiple in-laws moving there.
All right. Well, Sean, Tom, we're at the a little bit over time, but I appreciate you all sticking around and hanging out and having a conversation here. And but we're gonna wrap up. And just as a reminder, I guess I'll start with you, Tom. Where can people go to reach out to you, contact you, or learn more about what you're doing?
Yeah, so there's a number of talks that have shown up now on YouTube so that folks can see those and get really detailed information about how to do these
Yeah.
NEC calculations. And folks can always write me an email, Tom G. Kabat, Kabat @gmail.
All right. And
And
you're doing work with the Advanced Water Heating Initiative too, right? So I'm assuming.
right. So yeah, I try to help out a lot of different organizations who need these power efficient solutions to meet their goals. Yeah, I'm definitely spread fairly thin, but very interested in everything from policy. And we've got policy problems like the IRA is pushing money towards upsizing panels, and that'll jam up the grid. And I'm a grid planner and longtime utility person, so I'm trying to work on that nexus of how do we get all those needs met? Because we do
Yeah.
want the cold beer and the hot showers, and we don't want the delays of having to do and high rates of having to do all that upsizing twice or 3 times. We want to
Sure.
do it once on the distribution grid, but I'm working on policy analysis and all the way down through engineering and appliance requirements.
Great, great. And Sean, where can people go to contact you, reach out, or learn more if they'd like?
I put my email address in the chat, and I'll say it again. It's Sean Armstrong, PM, like the nighttime, PM @gmail.com. So I put Tom's in there, Tom G. Kabat at
Thanks.
gmail.com.
And you
Both emailers.
and you all do a retreat, right? A zero
Just
energy.
did that. Yeah, that
Oh,
was
just
awesome.
missed it. Okay. Yeah.
Nope. Yeah, and that retreat is like it's 50 people on the ocean, so it's not as easy to
Okay.
get into, but nonetheless, there's usually about 10, 15 people that squeak in
Okay.
that
Yeah,
I don't
and
specifically find.
well,
So
we also do
next.
the Ask Sean show.
Yep.
Okay.
That's
The
another
Ask John
fun
show.
series.
That's like once a month we do it. Like the Climate Reality Project sponsors it.
Yeah.
Anyway, if you guys are interested, reach out to us and we'll make sure that you get help with your single family or your multifamily or your program or with your community group. And,
Yeah.
Tom and I'd love to show up and help out.
Yeah. All right. Well, Tom, it was good to meet you. Sean, good to see you again as always. Be well and take care, everyone. Thank you so much.
All right. Thanks,
Thank you.
everyone.
Be sure to check out all of our courses available online that you can watch anytime and anywhere to pick up your CEUs. Before you go, make sure to subscribe to us on YouTube to get weekly updates and stay up to date on green building science courses, webinars, and home tours. Thanks again.